There we go. Okay, so we kind of covered a lot of these concepts last lab with the lab from last week, but going over it again, what is a bit? A bit is internally how your computer stores information. There's just a shit ton of bits in your computer. That's how it stores information. It's all in zeros or ones. So what values can a bit have? 0 or 1. The hardware is set up to like interpret all that stuff. We're not going to go over that, but it's all stored in bits. When you get to comp org, a little more of that will make sense. What numbering system base does binary use? So bits are stored as binary numbers, as 0 or 1s. Binary is base 2. So as humans on Earth in this class, most of us are used to base 10. Some other people probably use like base 12 or something because they feel special. But we got 10 fingers, so we started with base 10. And so you got like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we got 0 or 1. You guys covered a lot of that in programming 1, I'm assuming. With like base 2, base 16, base 8, and base 10. So yeah, numbering base for binary is base 2. So now these actual bitwise operators, there's AND, OR, XOR, negate. You guys have already seen in the context of like if statements and Boolean logic, AND, OR, and negate. So an AND is if both of them are true, it returns true. OR is if one of them is true, it returns true. And negate is it flips it. If it's true, it's false. If it's false, it's true. XOR is if they're different. And so it's XOR because it stands for exclusive OR. And so that means if both of them are 1, then it returns false. If both of them are 0, if both of them are true, it returns false. If both of them are false, it returns false. It's only if one of them is true will it return true. So that's what XOR is in the concept in the context of Boolean logic.
Wait, what did you say about OR again? Sorry.
What's up, Carrie?
What did you say about OR again? Like just the bitwise OR, normal OR?
So normal OR is just if either one of them is true, it returns true. Does that make sense?
Isn't that what you just said about exclusive OR though? That if one is true, then
no, exclusive OR is only if one of them is true. Both of them are true, it's false.
Oh, okay.
So if we can draw a truth table, which you've probably seen in discrete. If you've got A, B, and then there's OR and exclusive OR, it's not, that's just the symbols for them. If this is 0, 0, 0, 1, 1, 0, 1, 1, then over here, the OR is 0, 1, 1, 1, and over here, it's 0, 1, 1, 0. Make sense?
Mm-hmm.
Okay, cool.
And negate just flips it, whatever it is.
Yeah. So that's in the concept of Boolean logic. In bitwise, there's the specific concept of you do these between any data structures, and it goes bit by bit and returns the results of all those just as its own data type. So if you did an integer and an integer with bitwise, it would return an integer value just bit by bit. The result would be comparing bit by bit of the original 2. A good example of that is this wouldn't be integer. This would be, it's not even a real thing, but just if you had 1, 0, 0, 1, 0, and 1, 1, 0, 1, 1, and you did an AND operation between them, a horrible AND. If you did an AND operation, the resulting thing would be, you guys can't see. Guys, you don't have to look up.
I can see.
No, not the in-person people.
Oh.
I always fuck this up because I don't pay attention. Yeah, you guys should only.
I was like looking over here.
Yeah, this is, hopefully this is easier to see than over there. If it, now you have it in both places. So that's really the benefit. Okay, sorry. So back here, so if you had something that stored bits like these and you did an AND operation between them, it would result in the same data type, but with this as the result. That's because it just did a compare. So yes, no. Yes, no, no, yes, no. So that kind of thing. That's what I do. And so all of these bitwise operators do that bit by bit calculation. So it's not just results of a singular Boolean, it is all the bits inside of the whole thing. So that's an important note on those. For what the symbols all are, you've seen most of them, except for XOR and negate. So and is the singular. So for Boolean operators, and is the singular and, or is the singular vertical line. XOR is the up caret. So for me, that's shift 6 for whatever you got the equivalent. And then negate is the tittle. Tittle, whatever. That's for me, that's like the thing that's left of the one shift on that. Sure. Yeah. And I guess I technically did it wrong. It's that way. Beautiful. I'm an art major. Okay, so all those are the different things, and or XOR negate when it comes to bitwise operators. Any questions on those?
Nope.
Eric, I didn't have to do Dora the Explorer. Thank you. I recently learned, I saw someone doing this like Zoom teaching is the teacher playing Dora the Explorer. He's like, where's the thing? And it's a television, so you can't respond. It's like after 5 seconds, it's like, it's there. That's what it feels like, guys. That's what it feels like. Okay. Bit shifting. Oh, so yeah, bit shifting. We talked about that. The concept of bit shifting is just moving the bits left and right. So clear all. We had like a 1, 1, 0, 1, 0. If we shifted it to the left by 2, then we result in 0, 1, 0, 0, 0. We shifted it to the right by 2, we would result in 0, 0, 1, 1, 0. So it's just shifting the bits, and you fill the spaces with zeros.
I have a question.
What's up?
If you were to bit shift that number left by 2 like you did in the top example, and you shifted it back, would those ones come back, or are they lost?
They're lost.
Okay.
Good question. How does left shift work? Right there showed that. How does right shift work? Right there on the bottom showed that. So left up here, right down here. And I think I mentioned this last time that there's technically certain different, not philosophies, but ways you can shift. So you could fill it with zeros, you could fill it with ones, you could wrap around. The standard, if we ask you in an exam what you should expect to do if we don't specify, is zeros. And we don't talk about anything besides that in this class, so that's fine. But just in like future classes, if someone talks about bit shifting and they're like, fill it with ones, they're like, that's not bit shifting. It's like, kind of is. So just in this class, assume it's zeros, but don't be afraid if you see it in the future without. Left and right shifting is the equivalent of multiplying or dividing by what? So hopefully, if you got this question and had no idea what the answer was, but you were like, it's binary. What number do we think of when we think about binary? The answer should be 2. Yes. So hopefully, if anytime you're going to question about like what's the base or like what is it multiply divide by or anything about that kind of thing, a good default is 2.
Is the left shift the equivalent of divide?
Left shift is the equivalent of multiply. So if we clear this all, let's look at the number 0, 0, 0, 1. So that's the equivalent of 1. If we left shifted it by 1, that'd be 0, 0, 1, 0. That's the equivalent of 2. And then 0, 1, 0, 0. That's the equivalent of 4. And 1, 0, 0, 0. That's the equivalent of 8. So left shifting is multiplying by 2. Going in reverse, the right shifting is equivalent to dividing by 2. Does that also help answer your question, Carrot?
Yes.
Sure. So yeah, this is a very simple example. Even with bigger numbers, so like let's say it was 0, 1, 0, 1, left shifting. So this would be 1 plus 4 is 5. So if we shift it, that's 8 plus 2 is 10. So easy examples right there. There's a concept of overflowing and underflowing we're not going to get into now. You'll get into that in comp org and digital logic, which is when if we bit shifted if we shifted another time, it would be 0, 1, 0, 0, and we lose information there. So that is important to talk about, but we're not getting into that right now.
Is there a way you can do bit shifting with like floats to get the decimal value? Like I'm assuming there's like that's like a thing.
So floats are actually they're a specific format. They're stored in a specific format. The most common one being IEEE format, but it could be any format. But let's say floats for some reason we had a float that was represented by this. So the way floats work is we say, break up this information. The first bit is the sign. The next couple of bits are, what is it? It's the sign, the base, sign, sign, decimal, and exponent. That's what it is. So there's sign, decimal, and exponent. It's definitely, floats are a lot bigger than this, so it's that I'm giving a very simplistic example. But we basically say part of it's a sign, part of it is a decimal value, and part of it's the exponent, and you do sign is the sign. Decimal value is 1 point the decimal value. And then the exponent, so it's negative or positive, 1 point the decimal value times 2 to the exponent. And it's usually the exponent value minus like 147 to get it so it can be positive or negative. So bit shifting, you can still bit shift with floats, but it doesn't work in the same way of multiplying, dividing, because it's broken up into chunks like this. Integers are direct, they store the binary value they're representing. So it's a lot more easier to represent. Does that make sense?
Yeah.
Okay, so that was that. Multiply, divide. Awesome. Any more questions on shifting? Okay. So what is a bit field and why might we use one? So a bit field is like when we did with the lab. We gave you an integer value and we told you that a certain number of those bits represented the red, and another was green, blue, and alpha. So it was very easily 1 byte each, so 8 bits. But we could have also said like the first 10 bits represented a number and the next 10 represented another. And then so like we could have broken it up however we wanted to. It just very easily fits into 4 bytes, 1 integer value. You can do that. But the concept of bit field is using a data type like an int to store values that aren't the actual value of the int. It's something else. So the most basic case, most common case is Booleans. So Booleans, they are stored, like if you make a bool value, that's stored in a byte. So that's 8 bits. A Boolean can only be true or false though. So really there's a lot of excess going on there, but it has to be 1 byte because you can't store in a smaller chunk than that. So you couldn't just allocate 1 bit of information because there's not a memory address for that. It goes by bytes.
So a bit field is just like using bits to represent something other than like it's like literal or like it's whatever value, like its actual value. Okay.
Yeah. And so we use other primitive data types or an array to store other information. But so yeah, bool values by default are a whole byte, but we could say, hey, allocate space for a character and have each bit of that character, each 8 of those bits be the 0 or 1 represent the true or false of a Boolean. So you could use that information in that way. So if you're given a bit field that's 8-bit variable, how many bools could that represent? The answer would be 8 because there's 8, 0, and 1 values in there. Same with 16, same with 32. So it's just a direct 1-to-1 there. Now on the opposite end, if we gave you like, if you had an 8-bit bit field, how many integers could be represented in that? Integers in our language are 8 bits, 1 byte. So it would have to be that way. Does that make sense?
Mhm.
Technically, our integers are 4 bytes, so it wouldn't even be able to store them, like a character or something. But you get what I'm saying. Think about how many bits, how many bytes to bits. You should all know the printed data types, how many bytes they take, unsigned character, whatever. There's 1 byte, shorts are 2 bytes, integers are 4, floats are 4, that kind of thing. So however many bytes they have, you should be able to get the amount of bits they have from there and just think about math where can you put it in. Okay, yeah, so that's technically all for the bitwise operators we have today. Any questions on that? Okay, it is pretty straightforward. We talked about it a fair bit last time for last week's lab. Hopefully you can also help it for this week's lab, and I'll take any questions on that now too, if any of you guys have any issues with that. Have all of you completed the lab? Completed.
I did, yeah.
Matt's giving me a blank fucking stare. I don't know if that means yes or no.
Sorry, I did.
That means you didn't.
Yeah.
I'm assuming you don't have any questions. You just haven't done it yet.
Yeah.
And then Carrick said yes. I'm assuming all my other non-video participants are also in the yes. Oh wait, Carrick, you don't have your video on either. That's so sad.
I do now. I just forgot to put it back on.
How dare you? Oh, and here, let me make sure everyone can see. You guys couldn't see him either, right? Yeah, right, whole class discussion. Okay, cool. Awesome. So if there's no questions in the lab, no questions on the quiz study guide, then the rest of this period is going to be for project 3 assistance.
I think I have a quick question about.
Oh, Abigail, you have a question?
Yeah. So you convert everything into the RGB values, right? Can we store that into, oh, and then we store it into one big string, right? Those values together.
So I think actually the way that it's set up, let me go open it real quick. No, way too far back. Yeah, lab 8. Yeah, I can just download this.
Because I'm just wondering, like, after you store it, do you store it like, I'm thinking like as an object, and then you do the whole hex conversion, and then you store it into the map?
So yeah, you definitely should have a color object because we tell you to have one, right? I think
Exactly.
specific, yeah. So right here, this is what your color object should have. So you store unsigned character for the RGB. That's what should be stored.
Yeah.
Yeah. So what was your question?
But prior to converting it into hex, we should have the RGB value like all in one string together, should we? So like R next to G next to B in one string.
I mean, if you that's up to you if you want to store it like that. I don't see anything in here that like requires that.
It says
But,
on the top, it says to convert it to string. So that's what I was just trying to clarify.
What's the convert to string thing?
Go up. Okay, so where it says hexadecimal conversion. Okay, yeah, the first line. It says store it in a string representing well, but that's, I guess.
So yeah, you convert to hexadecimal and then store the hexadecimal as strings because you do have to have the hex value as a string right there.
Yeah.
So that's true, but I don't think it says anywhere that you have to store it as like the integer values into a single string.
So maybe like we could convert each one individually and then store them all into one big string.
Yeah, that's fine. Because all the things you have to print out the name, this hex string right here, and then the individual RGB values separated by commas.
Yeah.
So.
Awesome. Thanks.
Okay.
That was my question.
No problem. Any other lab 6 months then? Abigail, you came out of not left field, but you took a second to get that. So now I was making sure, just so I can shift mental gears. If I have to shift back, that's fine, but my brain is a slow machine. Yeah, lab 8. Any other lab 8 questions? Okay. With that, I am going to stop recording.